Welcome to the video on Computer-Aided Drug Delivery Systems, CADDs. This is Unit 3, Part 2, presented by Dr. Krishna Yadav. This video will focus on computer-aided formulation development and pharmaceutical optimization. We will examine computational science, mathematical optimization, and the regulatory frameworks that drive modern pharmaceutical research and development. Optimization technology uses computational methods, algorithms, and mathematical approaches to solve formulation optimization problems. Major technologies include classical optimization, Lagrangian method, linear programming, canonical analysis, artificial neural networks, genetic algorithms, and the desirability function. Classical optimization involves direct analytical methods based on calculus to find maxima or minima. It works well for simple, well-defined systems, such as optimizing drug release modeled as a quadratic function. However, it is not suitable for complex, multi-factor pharmaceutical systems. Classical optimization easily finds the global optimum in simple, well-defined functions. However, complex multi-factor systems have many peaks and valleys, causing simple derivative-based search methods to get stuck on false local maxima, failing to find the true global optimum. Classical optimization is ideal for simple, single-variable problems with a clear mathematical model. Its principle is to find maxima or minima by setting derivatives to zero. The limitation is that it cannot handle the complexity of real pharmaceutical systems. The Lagrangian method is key for balanced formulation design. It uses the Lagrange multiplier to find the highest feasible optimum, ensuring both objective and constraint are satisfied. This allows optimization while meeting regulatory or compositional limits. The Lagrangian method is essential in pharmaceutical formulation, where multiple limits must be respected. It helps find the best formulation that gives the maximum or minimum desired response within allowable limits, balancing performance with regulatory and composition constraints. Linear programming assumes a linear relationship, which often contrasts with the actual nonlinear behavior common in drug delivery systems. This method finds the optimal solution within a feasible region defined by linear constraints, but fails to capture essential curvature effects. Linear programming is a mathematical method used to optimize a linear objective function, subject to linear constraints. It is useful for resource allocation and blending problems, but its major limitation is the inability to capture nonlinear behavior and interaction effects in real-world systems. Canonical analysis is a specialized tool used in response surface methodology, or RSM. Its purpose is to determine the nature of the response surface, whether it is a maximum, minimum, or a saddle point, by transforming the quadratic model into a simpler form to interpret curvature. Canonical analysis helps visualize and interpret the optimized surface. It distinguishes between a true maximum or minimum and a saddle point, which is a false optimum. The process involves transforming the initial model into a simpler canonical form for curvature analysis. Canonical analysis is a critical tool in pharmaceutical applications to verify the true optimum. It transforms a complex quadratic model into a simpler form and uses eigenvalues to classify the stationary point as a maximum, minimum, or saddle point, preventing false conclusions. Artificial neural networks, or ANNs, are a machine learning tool inspired by the human brain. Key features include handling complex, nonlinear relationships and learning from experimental data. Pharma applications include predicting drug release profiles and nanoparticle size. ANNs learn from experimental data to handle complex nonlinear relationships in pharmaceutical applications like predicting drug release. They offer an advantage over polynomial models in complex systems, but their main limitation is the black box nature, making them less interpretable. ANNs mimic the human brain using interconnected neurons. They capture highly nonlinear and interactive effects, learn from data, and are used in pharma to predict drug release, nanoparticle size, and stability. While more accurate than polynomial models, their black box nature is a limitation. Genetic algorithms, or GA, are an evolution-based optimization technique that mimics natural selection through selection, crossover, and mutation. GA works by iteratively improving multiple solutions to find the global optimum. They are often coupled with ANNs, or RSM, for multi-objective optimization and complex formulation design. Genetic algorithms are inspired by natural selection, using evolutionary operators to maintain a population of potential solutions based on a, quote, fitness function. In pharma, they find optimal formulation compositions, excipient blends, and synthesis parameters. They can find global optima in complex spaces, but have a high computational cost. GA is a powerful global optimization tool, especially when a model equation is not known. It uses a fitness function to assess solutions and evolutionary operators like selection, crossover, and mutation to iteratively improve the population over generations, ultimately leading to the optimal solution. The core of the genetic algorithm process involves evaluation, selection, crossover, and mutation to create a new generation of solutions. This cycle repeats until the population converges to the optimum. GA is known for finding true global optima, but often requires high computational resources. The desirability function transforms each response into a desirability value between 0 and 1. These individual desirabilities are then combined into a single overall desirability index, which is maximized to find the optimal formulation that balances all quality attributes. This method is useful when multiple targets must be met simultaneously, such as optimizing both drug dissolution and tablet hardness. The desirability function provides a single score to guide the optimization process toward the most balanced and ideal product. Screening designs for factor identification includes Plackett-Berman design and fractional factorial design. PBD screens many variables in few runs, but effects are highly aliased and cannot be used for optimization. FFD uses a subset of full factorial runs, and its resolution dictates the degree of confounding, making it more robust for identifying key factors. This video utilized references from ICH guidelines, key texts on experimental design, and pharmaceutical development literature to cover the essential aspects of optimization technology in computer-aided drug delivery.